this is the Riemann-Zeta function's functional equation. Now, the Riemann-Zeta function is commonly known throughout the math community, right? It's like, most people know it as the function that goes 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, and so on. Now, there are some inputs for s that just don't make sense, right? Say, if you tried zeta of -1, then it would just be 1 plus 2 plus 3 plus 4, which obviously diverges, right? It heads off to infinity, and you can't assign a value for it, so it should be undefined. But as many of you guys also know, there is an analytic continuation of the Riemann-Zeta function into these territories, right? But so that means there is a value that can be assigned to this, and many of you guys may know that that value is -1/12. How do we get there though? Well, you know that if you just plug it straight into here, right? Just take a look at this by itself. Plug it straight into its definition. It's not going to work, obviously, because, you know, it diverges. But this is its functional equation, which we will soon derive. It is always true for all values of s, right? So if -1 doesn't make sense on its own on the left-hand side, just plug it into the right-hand side, and the right-hand side will give you an answer that is actually defined. Yeah, because notice that if you plug in a -1 for each of these, it all outputs a number that makes sense, right? 2 to the -1, pi to the -2, and especially these two. These two are important. Gamma of 1 minus -1 is gamma of 2, which is a number that does indeed exist, and zeta of 1 minus -1 is zeta of 2, which is also a number that does indeed exist. And if you do plug it in, you'll see that it does indeed give you -1/12. So that's how we use this equation, right? It's a way of just continuing the Riemann-Zeta function into numbers that traditionally would not work. So with that in mind, where does this equation come about? Well, let's start with the gamma function. Now, the gamma function integral definition is this. It's defined as the integral from 0 to infinity of t to your input, and in this case we're going to be using s, minus 1 times e to the -t dt. Now, gamma function is commonly known as an extension of the factorial function. However, we're not going to be using it as that. Here, we're going to be using it to try to achieve this equation up here, which is going to take a while. So just stick with me. And a lot of the steps that I'm going to be taking in this video are kind of unmotivated, right? Like the next one where we plug in s/2 instead of s. You're just going to have to stick with me on that. So yeah, let's take the next step. Let's plug in s/2. So if we just go ahead and replace all of the s's with s/2, on the right-hand side, it's still the integral from 0 to infinity, t to the, instead of s, we have s/2, and that's the only difference. Okay, and another unmotivated step that we're going to take is to make a substitution. And that's to this integral right here. We want to write it in a slightly different form, but it's still equivalent to this. Let's let t equal to n squared pi x. It seems like a random jumble of numbers, but eventually it'll make sense. And I'll point out when. But for now, let's just try to work through this, right? We have our t, but we don't have our dt. So let's differentiate both sides. The derivative of t is just dt, and the derivative of n squared pi x is just n squared pi, and then derivative of x is dx. So that's our differential. So the right-hand side is equivalent to, and we also got to change up the bounds. So when t is equal to 0, then x also has to be equal to 0. And then when t is equal to infinity, then the right-hand side, one of the factors also need to be equal to infinity. And since n squared pi is not infinity, obviously, x has to be infinity too. In here, t, we just go ahead and replace that with n squared pi x. And our exponent is still s/2 minus 1. And then e to the negative t, but t is n squared pi x. And then our dt is n squared pi dx. There we go. All right, next, we want to consolidate this integral down just a little bit. So that means we pull out whatever's constant, right? So anything that doesn't have an x in it, for example, n squared pi, and we can maybe break this guy up, right, into two sections. The first one, we can have just n squared pi, so that's a constant, and then we just have the x. So yeah, let's go ahead and break this up first, just this guy. So if we break it up into one factor with n squared pi to the s over 2 minus 1. And in fact, I'm going to copy down this factor right here, right next to it, for a pretty obvious reason, because they have the same base, so we might as well combine it, right? This is basically to the first power. But we'll do that in a second, and then we still have the x, right? And it's still to the same exponent, and then we have our exponential e to the negative n squared pi x, and then we have our differential dx. So right here, these two have the same base, so we just add the exponents, right? Negative 1 plus 1 is just 0. So basically, these just cancel out, and you're left with n squared pi to the s over 2. So you can kind of, do that. You're left with that, but that's a constant in terms of x, right? Our integrals in terms of x, there's no x inside of this, so let's move it to the outside. Moving it to the outside, it looks like this. N squared pi. And then we've got s over 2. And then on the inside, we still have all the remaining stuff. Okay, so now we have this. And I want this integral by itself, so let's just go ahead and divide both sides by this. But before we do that, notice that there's still kind of two factors inside of this, right? We have n squared and we have pi. We can just go ahead and distribute the power. So just focusing on this by itself, and distributing the power, you have n squared to the power of s over 2, which is just multiplying the powers, right? Notice that the 2's cancel, you just have n to the s. And then the pi, not much you can do about that. So it's just pi to the s over 2. Okay, so you have n to the s times pi to the s over 2. You got the integral by itself, so let's divide this on both sides. So on the left-hand side, we still have our gamma function of s over 2 on top. Now, in the denominator, you have n to the s, pi to the s over 2. And you can see where the zeta function is starting to play in here, right? You have 1 over n to the s on the left-hand side, just sum over n is equal to 1 to infinity on both sides, and you'll be done. And, well, no, not you'll be done. You'll have the zeta function pop out. Now, on the right-hand side, it's just going to be the same integral. Okay, so now, as I mentioned, we're going to be summing over n on either side, right? So left-hand side, doing that summation, going from n is equal to 1 to infinity, we'll turn this one over n to the s into the zeta function. So I'm going to just write down the zeta function. So on the left-hand side, this sum of 1 over n to the s now becomes zeta of s. We still have the gamma function, so gamma of s over 2. And then we have this over pi to the s over 2 in the denominator. And on the right-hand side, also, we notice that we also sum over the integral. However, by Fubini's theorem, you're summing over an integral, right? You can interchange the order of summation and integration. So, let me check my notes. Okay, yeah, just interchange the order. Now, we can put it here between the integral bar and the x to the s, and the power, right? So, integral from 0 to infinity. But do we really want to put it there, right after the integral sign? Because you see, this factor right here, this x to the s over 2 minus 1, is not in terms of n, right? There's nothing in terms of n inside of it, whereas the summation is entirely in terms of n. So, in a way, you can kind of factor that outside of the summation because, it has nothing to do with it. You just have x to the s over 2 minus 1. Then you have your big sum going from n is equal to 1 to infinity. And then all that's left is this. The exponential is the only thing that has an n inside of it. E to the negative n squared pi x dx. All right, so that's what we have. Now we're going to be focusing in on the right-hand side. Okay, so by convention, we notice that, not even by convention actually, we notice that this guy right here is really similar to a function that pops out commonly in many applications, and that is the Jacobi theta function. But more specifically, the analytic number theory interpretation of it. Basically, recall that theta, which I think you write like that, of x is defined as summing over the integers. So basically, instead of n is equal to 1 to infinity, you start at negative infinity and you go to infinity. So all the integers of e to the negative n squared pi x. Right? So this and that look extremely similar. So let's give this guy a name. Let's call it xi, right? And let's put this down on the side as a quick note. Let xi of x be equal to this function in here. Very similar to the theta function, but not exactly the same. And there's a few reasons why we want to do that. This right here, we're going to be treating it as a function with some of its own properties to be able to move on to our next steps. And am I going to run out of room? All right, e to the negative n squared pi x. Okay, so from here, let's go ahead and replace this guy with just xi of x, right? This is just the integral from 0 to infinity of x to the s over 2 minus 1 times xi of x dx. Okay, now I want to break this integral up into two intervals using the linearity of the integral. So let's integrate from 0 to 1 first, right? So 0 to 1, and then we have the integrand. And then the rest of the way from 1 to infinity. Okay, so this is kind of what we have. And now the reason why we did this is because I want to leverage some symmetry on this integral right here. 0 to 1, we can make that 1 to infinity, right, by using a substitution. And inside of here, there's also some pretty nice stuff that pops out. Just wait and see. For this integral specifically, only this first one, let x equal to 1 over u. Or in other words, u to the negative 1, right? And its differential, if we differentiate both sides, the derivative of u to the negative 1 is just negative u to the negative 2 du. And next, the bounds, right? We need the integral bounds. When x is equal to 0, well, u has to be equal to infinity, right? Because 1 over infinity approaches 0. So this lower bound has to be infinity. U equals to infinity when x equals to 0. And when x equals to 1, then u also equals to 1. Because 1 equals 1 over 1, obviously. All right, inside of here, I'm going to replace this x with u to the negative 1. And then our exponent is going to stay the same. We now have xi of, instead of x, I'm going to write 1 over u this time. And then our differential is negative u to the negative 2 du. Okay, so first of all, notice that this bound is backwards, right? We're going to use this negative sign right here to flip it. So instead of infinity to 1, we're going to go the right way around, 1 to infinity. So now our bounds are equivalent between these two integrals. Other thing is, there's a lot of stuff you can do here. Inside of this factor in of itself, the powers can multiply. So what you get is u to the negative s over 2 plus 1 once you multiply the powers. Here, u to the negative 2, if you combine these guys, right, well, they have the same base, so the powers add. 1 minus 2, 1 plus negative 2 is just negative 1. So u to the negative s over 2 minus 1. So this entire thing and that entire thing just becomes this. So, yeah, let's put it over here. this becomes the integral from 1 to infinity of these two become this. So u to the negative s over 2 minus 1. And then we still have this xi of 1 over u term left. And then our differential du. So this integral is equal to that one. So let's just put that down again right underneath it. And then we can deal with some stuff having to do with the xi and the Jacobi theta function that I put down earlier. Okay, I just moved this guy up here. No big issue. One thing, I'm going to rename this u to x because we want to be working in the same variable. Now I know x and u are related in a different way, but this is basically just renaming the variable, right? You're not changing the value, we're just renaming it. So if we just go ahead and replace all the u's with an x, this still represents the same exact value. You're just using a different dummy variable. Okay. So now what? Now we know how to deal with this guy, right? It's just that function up there, and we're more familiar with it because it looks similar to this. But we want to find a way to rewrite this. We now have the symmetry, but we do have this weird thing in the middle here that is, you know, kind of uncomfortable. So how are we going to do that? Well, we know that this xi of x is very similar to this theta of x, and we also know that this theta of x has a special property, and that's its functional equation. It's equal to 1 over the square root of x times the theta of 1 over x. So we're going to be leveraging this property later on, since this kind of corresponds with this xi of 1 over x, and this kind of corresponds with that. But first, we need to connect these two functions, right? And how are we going to do that? Well, let's expand out theta of x and see what we get from it, right? So there's a lot of terms, right? But I want to focus on the ones that are close to 0 because, you know, that's where we might find some symmetry. So let's start with n is equal to negative 2. So we have dot, 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 plus, 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 whatever. Dot, 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 right? So this is kind of cramped, but you can see what's going on. Now notice that this is actually symmetrical. This guy in the middle right here is just 1, right? So replace that with 1. But notice that this integral right here and this integral are exactly the same. And this, sorry, not integral, term. This term and that term are the same because negative 1 squared is the same as 1 squared. And same with this thing and that thing, right? Because negative 2 all squared is the same thing as just 2 squared. So basically, it's symmetrical about the center term, this whole function. So the way you can write it is as, let's put the 1 up front, but there's 2 of these guys now, and there's 2 of these guys now, right? We just combine like terms because they represent the same value. 1 plus 2 times, and this is just, let's just write it as this, right? E to the negative 1 squared pi x. And then plus 2 times e to the negative 2 squared, because, you know, these are equal, pi x. So there's 2 of them. Plus 2 times e to the negative 3 squared pi x, and then so on. Okay, now notice there's a 2 in each of these terms. So what we can do is go ahead and just factor that out, right? If we factor out a 2, then what are we left with on the inside? E to the negative 1 squared pi x plus e to the negative 2 squared pi x plus e to the negative 3 squared pi x. We're left with this, our xi of x, right? Because notice that if you just expanded our xi of x, you'd have e to the negative 1 squared pi x plus e to the negative 2 squared pi x plus e to the negative 3 squared pi x, and so on. So this thing in here is just our xi function. So we have found a relationship between the Jacobi theta function in the analytic number theory sense, of course, not the multivariable sense, and our xi function. So let's write that down. Theta of x is equal to 1 plus 2 xi of x. Very simple linear relationship. Okay, so what was our original goal? We have found the relationship between these guys, right? Our original goal was to find a replacement for this in terms of that. So how are we going to do that? Well, if theta of x is equal to that, then just take a look at this right here, right? This is a relationship, we can go ahead and use it. Now, by because we know the relationship between theta and xi now. So let's just go ahead and replace everything that's in terms of theta with stuff that's in terms of xi. Now, one quick thing I want to do is get the square root of x out of the denominator by multiplying it on both sides. So you now have root x times zeta of x. On the other side, you just have theta, of 1 over x. Okay, so that's the relationship you have. Now, theta of x is obviously 1 plus 2 xi of x, as we deemed earlier. So this is just square root of x times 1 plus 2 xi of x. And on the right-hand side, we can use the same thing, right? Just replace everything inside of here, all the x's, with the 1 over x. So that would just be 1 plus 2 xi of 1 over x. So there you go. We found a relationship between this guy and that guy. So thank you, Jacobi theta function. Okay, where do we go from here? We got to isolate this guy. So just distribute in the square root and subtract the 1 on both sides, and you get this, right? Distributing the square root into these two terms, right? And then subtracting a 1 on either side, just divide everything by 2. So now we found a functional equation for our xi of x. So go ahead and plug this guy into here. And it might seem pretty big and bulky, but it'll give us more room to work with. So what I'm going to be doing is replacing this guy, right, with this guy, because they're equivalent. And we still have our other integral here. Alright, so I made a small correction there. There's a negative sign. Other than that, everything looks good. Now, if we expand this, let's, distribute this in. So now this turns into 3 terms. And we can also turn into 3 integrals, right? Break it up into 3 integrals using the integral's linear property. I just dropped an eraser. I hope my floor doesn't get fucked up. Now with this first term right here, we have this guy times root x, so that's x to the 1/2, right? Times xi of x. But really quickly before we continue, these two factors have the same base. So if we combine them, then the exponents add. So -1 plus 1/2 is just -1/2. So in reality, we can just condense that into negative s over 2 minus 1/2, and we still have our xi of x dx. All right, I'm going to write this term down first, because this term and that term both have xi of x's. Okay, and then next we have these two terms in here, and they can kind of be grouped because they both have a factor of 1/2, right? And now one thing, once again, just like we did with the first term, the square root and this can be combined. The square root of x is just x to the 1/2, and combining them, you get -1 plus 1/2, which is -1/2. So that square root of x can be consolidated up into the exponent of this guy, so negative s over 2 minus 1/2. And that looks right, so all we have now is a factor of 1/2, which I'm going to move to the outside, and then we can close this off with the dx. And then we have our last term. I'm going to also move the 1/2 outside, and this one is very basic and very simple. Okay, so that looks good. Now, notice that we grouped this for a reason, because we can now combine the integrals. All of them have the same bounds from 1 to infinity, and factor out the xi of x. And we can group these guys because they're both integrable, right? So we can just go ahead and integrate them right now if we really wanted to. So I'm going to combine these guys, factor out the xi, and I'm going to integrate these. Okay, so I wrote down the first two. Now let's integrate these respectively. Let's work on this term first. So this is obviously just a case of reverse power rule. You can use some properties, but I'm just going to raw dog this. All right. The 1/2, I'm going to keep it on the outside. Now, integrating this guy on the inside here, we add 1 to the power, so that gives us negative s over 2 plus 1/2. And then we divide by the new exponent. All right, and we have to go from 1 to infinity, obviously. Okay, and then now the second term, same idea, add 1 and divide by the new exponent. Okay, and let me check my work just to make sure everything is right. No, one thing, right, yeah, let me check my work. Okay, so I'm glad I caught this. There's one mistake. This right here came from subtracting 1 on either side, right? So it's supposed to be a negative sign, but that's okay because we can just go ahead and make that change throughout. This negative 1/2 carries down to here, right? We distributed it in. And this one we factor out the xi. Over here, integrating this now, instead of a positive, we should have a negative. So that looks good. Yeah. Now we can do some cancellations since we have complex fractions. Now, this 2 distributes into this denominator, right? So it cancels with the denominators of the denominator, which are all 2. And same thing over here, right? This 2 cancels with that 2. And the double negative makes a positive. Okay, so what do we have now? I just want to focus on these two terms. We now have just x to the negative s over 2 plus 1/2, which we can rewrite as 1 minus s all over 2, right? And then over here, and don't forget we have the denominator of 1 minus s. And over here we have the positive plus x to the negative s over 2 over s. All right. So now we gotta, these both go from 1 to infinity. So we gotta plug in bounds. I'm gonna move this back up there. Actually, you know what? Just erase some stuff right now. And let's plug in the bounds. So, this one right here, if we plug in infinity into x, we know that if the exponent here is negative, so basically, if the exponent here is negative and x approaches infinity, then this whole thing goes to 0, right? Think infinity to the power of negative 1. That's 1 over infinity, that goes to 0, right? So as long as the exponent is negative, then it's gonna crash out. So this exponent has to be less than 0, meaning s has to be less than, greater than 1, right? And that makes sense given the context of a Riemann zeta function. Traditionally, it's only defined with s being greater than 1, right? So if we make the assumption that s is greater than 1, then it'll go to 0. All right. So this first term goes to 0 when you plug in infinity. So you kind of have 0. Let's just write that down. Plus, now we already know that we have the condition that s is greater than 1, meaning this exponent, regardless of what s is, regardless of any other conditions, we already know that s is greater than 1, meaning this exponent is always negative, meaning if you plug in infinity to the negative exponent is 0. So this thing goes to 0 too. 0 plus 0. All right, now we subtract off plugging in 1. Plugging in 1 to here, 1 to anything, 1 to the any power is going to be 1. So you have 1 to the 1 minus s, and plus, same thing with this, right? 1 to the anything is always going to be 1. So you still have 1 over s. Distributing the negative sign, this becomes negative 1 over 1 minus s minus 1 over s. Okay, so I'm going to rewrite everything. This I'm going to keep, but I'm going to replace these two terms with this result that we came up with. Okay, so all I did was rewrite everything up here and replace the two integrals that we integrated, and we found it was equal to that. Now, let me think. Yeah. All right, so you may notice some stuff about this right here. In fact, I want to deal with this integral right here just a little bit. Now, I'm talking about this factor right here. I want to factor out a 1/2, right? Sorry, not a 1/2, a 1 over x. Factor out a 1 over x is just decreasing the exponent by 1. So you need to add 1 back. So you want to add 1 to each of these because you just factor out a 1 over x. So what you get is x to the negative s over 2. Negative 1/2, add 1 becomes positive 1/2. So another way of writing this is 1 minus s all over 2. So this is what you get after you factor out 1 over x. And over here, adding 1 back, you just get x to the negative s over 2. All right. So I'm going to rewrite this integral really quickly. Okay, so I rewrote it. I'm going to move this 1 over x, multiply it with the dx, so just write dx over x, right? That's a common property in integrals, having a dx over x. So in here, now everything looks just a little bit cleaner. I'm going to do minus 1 over 1 minus s, minus 1 over s, right? That's the remaining two terms. All right, why did I do that? Well, notice that if we replaced all of the s's instead with 1 minus s, we still get the same expression back, right? So we found a symmetry. Regardless of whether we plug in s or 1 minus s, we get the same expression. And I'm going to walk this through a little bit. Yeah, so if we just go ahead and do this for a second, I'm going to copy down stuff. Okay, so we have our first instance of an s. 1 minus s, but we have to replace s with 1 minus s. So it looks like this. Notice that this 1 and 1 cancel, and this double negative s just gives you a positive s. So you have an s, and I'm pretty sure this guy right here is positive. Yeah, it's supposed to be positive. I think I copied that down wrong, that's all. Yeah, this came from the second term, which we didn't touch at all when we were manipulating the xi. So that s should be positive. My bad. Okay, but this 1 minus s becomes just an s after you make this substitution. All right, the next term, x to the, well, just go ahead and replace all s's with 1 minus s's, right? So that's pretty simple. Dx over x. And then we have these two. Same deal here, right? If you replace this s with the 1 minus s, same math goes on as went here, right? You're just going to get an s back. And then last term, same deal. You replace all the s's with the 1 minus s. So notice, because addition is commutative, if we just swap the order of this, we get that back. And if we swap the order of this, we get that back, right? So that means if we plug in s or 1 minus s, it's always going to be true. So now I want to connect this back to the other side of the equation. That means if you go ahead, since this expression is always equal to this expression right here, then this property right here, you can reflect over s and 1 minus s, is also going to be true for this side, right? Yeah, since this guy right here is equal to that, as we saw originally, right? But here, we're going to take the other side and replace all the s's with 1 minus s's. So yeah, since these are equal to each other though, right? Because, just swap the order of addition. It's the exact same expression. That means these are also equal to each other. So that was the whole point of doing this integral exercise. It was to show that this expression right here, regardless of whether you plug in an s or 1 minus s, it's going to be equal to the same value. So I'm going to copy this. Since these are equal, that means these are equal. I'm going to copy that up here. Okay, so I copied it down. Now this is what we're going to be working with, I hope. So yeah, okay, let's get started. Now notice that in our final result, zeta of s. Zeta of s is isolated, right? So now let's try to isolate zeta of s. Pretty self-explanatory. First, I want to make some changes. If we put this guy in the numerator, we have to make the exponent negative, right? So this right-hand side right here is equal to zeta of 1 minus s, gamma of 1 minus s over 2. But if we want to put the pi up there, then we're going to have to negative the exponent. So instead of 1 minus s over 2, we're going to have s minus 1 over 2. All right. And we can, in fact, we can break this up. S over 2 minus 1 over 2. All right, so now we can do stuff. Multiply this pi of s over 2 on either side. And dividing this gamma of s over 2, we can isolate zeta, right? So multiplying this pi of s over 2, we just get another pi of s over 2, right? But because these two factors have the same base, the exponents add. S over 2 plus s over 2 is just s. So that's pretty simple. These two factors, gamma and zeta, are still going to be there. Okay, now as I was saying, pi, it's going to be to the s minus 1/2. And we divided both sides by this gamma of s over 2. Okay, cool. So now, it kind of looks like we're stuck, right? But we have a formula called the Legendre, I don't know if that's how you pronounce his name, duplication formula. And it's one of the functional equations for the gamma function. And I'll just write it out, and I'm going to prove it in a second. But here it is. The Legendre duplication formula is gamma of z times gamma of z plus 1/2 is equal to 2 to the 1 minus 2z square root of pi gamma of 2z. Okay, seems just like a bunch of random shit thrown together, right? But I mean, at least it's going to get us our 2 to the something out. This pi might help too, right? So we can just use it, but I want to prove it. First, we start with the beta function. Now, the beta function is known as the Eulerian integral of the first kind, and it's an integral, and it's a function of two variables. So, beta of x comma y, right? And here's its integral definition. We're integrating from 0 to 1, and our integrand is u to the x minus 1 times 1 minus u to the y minus 1 du. So this is the beta function. We also know that another definition for the beta function is we can express it using the gamma function. So we know that beta of xy is equal to gamma of x times gamma of y over gamma of x plus y. And I might prove this in a future video, but as of right now, I'm not gonna, because this is just another rabbit hole that we can go down. And we're kind of already in a rabbit hole, the Legendre duplication formula. We could just use this, but I'm choosing to prove it. So anyways, yeah, so we have this property right here. So that means if you go ahead and plug that in to where the beta function already is, gamma of x, gamma of y, gamma of x plus y, then it's also equal to that integral right there. Another thing right here is that instead of x and y, I'm going to plug in z for both of them, right? So if you instead plugged in z for x and y, that would give you beta of z comma z. But we're more concerned about what's going on here. So let's go ahead and plug in a z for both x and y. Now up top here, since you now have gamma of z times gamma of z, it's going to be gamma squared of z. Okay. And at the bottom, gamma of x plus y, gamma of z plus z is gamma of 2z. So that's the left-hand side. On the right-hand side, both of the exponents are now going to be the same. So if we wanted to, we can go ahead and multiply the bases, right? So it's going to look like this. U times 1 minus u. And then both of the exponents are just going to be z minus 1, right? X minus 1 becomes z minus 1. Y minus 1 also becomes z minus 1. So we can combine them. Okay, the next step is to make a substitution. U equals x plus 1. All right. Now we let u equals x plus 1 over 2, sorry. Okay. If we take the derivative on both sides, then du is on the right-hand side, we have this 1/2, right? That goes to 0. X over 2, the derivative of that becomes 1/2 dx. So we can just kind of write dx over 2, right? So that's kind of what's going on. Now we put the bounds down. When u is equal to 0, so if this is equal to 0, then x has to be equal to -1. That zeroes out the numerator, so 0 is equal to 0. So this has to be -1. And u is equal to, when u is equal to 1, then x also has to be equal to 1, since 1 plus 1 is 2. 2 over 2 gives you 1. So the bounds are now symmetrical. All right. In here, u becomes x plus 1 over 2. And then 1 minus u, well, that becomes 1 minus x plus 1 over 2, right? But we can make this 2 over 2 minus x plus 1 over 2. This 2 minus 1, well, actually, if we distribute this negative sign right here, see the x becomes negative, but 2 minus 1, more importantly, is positive 1. So this right here becomes, the x becomes negative, and 2 minus 1 is positive 1, so 1 minus x over 2. So plugging x plus 1 over 2 into this second factor right here, then whole factor becomes 1 minus x over 2. Okay, and then the exponent is still z minus 1, and du becomes dx over 2. All right, so that is our substitution. Next step, notice that these two are difference of squares patterns, so obviously they're conjugates, so multiply them together, it becomes a difference of squares. So the integral bound is -1 to 1. Inside of here, it becomes 1 squared minus x squared all over 2 times 2, which is 4. So 1 squared is just 1 minus x squared all over 4. And this whole thing is to the z minus 1. And then we have dx over 2, which I'm going to move to the outside, 1/2, right? Notice that you can break this guy up on the inside here. Distribute the power onto the numerator and the denominator, and you get, distributing the power into the denominator, it just gives you 1 over 4 to the z minus 1. So, and that's a constant in terms of x, so let's bring that outside. So you get 1/2, and then bringing this outside, 1 over 4 to the power of z minus 1, which you distribute on. And then we have our integral from -1 to 1 of 1 minus x squared to the z minus 1. All right, and you still have your dx. Okay, now here, I think this is where it gets front. Oh yeah, you're also able to simplify the front down a little bit. I'm going to move this back up here. Hopefully that doesn't mess up anything I was going to use. All right. So this, let's write down the left-hand side again. Gamma squared of z over gamma of 2z is equal to, on the right-hand side, we can simplify this down a bit, right? So right now our coefficient is 1/2 over 1 over 4 to the z minus 1. 4 is just 2 squared, right? 2 squared to the z minus 1. This 2 distributes onto both terms in the outside power, so 2 to the 2z minus 2. Gotta make sure my phone is still recording, just thought of that. Okay, thank God it is. Alright, now you still have this 2 being multiplied on the outside, right? That comes from here. This is kind of 2 to the 1, right? 2 to the 1, since the bases are the same, they're both 2, then the exponents are going to add. So 1 plus negative 2 is just negative 1. So this whole denominator becomes 2 to the 2z minus 1, if I'm not wrong. And if we flip it into the numerator, then the exponent becomes negative. So order of subtraction reverses, you just get 2 to the 1 minus 2z. All right, that's where this guy comes from, kind of. So the coefficient out front becomes 2 to the 1 minus 2z. I'm going to erase this work now. Down here, you have your integral, which is also kind of special to us because of an identity I'm going to derive in a second. I'm going to copy this down. Okay, so what is the identity? Well, first of all, notice that the integrand is even, right? How do we prove this? Well, if you plug in, say, negative x here for, if you plug in a negative x, is it still going to be the same function? And obviously it is, because the entire x is inside of a square, right? So if you plugged in a negative x, the negative x squared is always going to be equal to x squared. So when you plug in a negative x, the function stays the same. Therefore, the integrand is even. And recall this property. If you're integrating from negative a to a, and your function is even, right, and it's in terms of, say, x, then that is equal to integral from 0 to a of, what was it? The same function? No, the function over 1/2 times this right here. And there's a pretty easy visual intuition. Basically, it's just the same thing. You can, an even function you can reflect over the y-axis, right? So it's the same area on either side of the y-axis. Also because your bounds are symmetrical. So you're going the same distance away from the y-axis, and the area is the same under both sides. So what you can do is you can just find the area under one side and double that, right? Since it's the same on the other. So actually it's just not 1/2, it is 2 because you're doubling the area. So that's how intuition helps, right, obviously. But we can apply this property now. Obviously the outside's still gonna stay the same. No, because there's a 2 multiplied there now. So multiplying a 2 on, you get, I'm gonna write this out again, 2 to the power of 1 minus 2z. If you multiply 2, it's 2 to the first, right? The bases are the same, exponents add, you get 2 minus 2z. Very simple. Okay, now we use this property. Instead of going from negative a to a, we go from 0 to a. So we start at 0 and go to a, and in our case, a is 1. And then everything else stays the same. So 1 minus x squared z to the z minus 1 dx. Okay, cool. Another property that we're going to derive, and we're once again going to start from the beta function. So beta function, let's write it, the definition out. Beta of x comma y. This is equal to, let's write out the integral definition. Integral from 0 to 1, u to the x minus 1, 1 minus u to the y minus 1. Alright, I already explained that earlier. But now, we make a different substitution. Instead of u equals 1 minus x over 2, or whatever we did earlier, we're going to let u go to t squared. Here's how that's going to work out for us. So let u equal to t squared. Differentiating both sides, du, on the right hand side, 2t dt, right? Okay, so let's go ahead and plug it in. The bounds are still going to stay the same, right? Obviously, because this is 1. 1 is equal to 1 squared, so t is equal to 1 when u is equal to 1. And same thing with 0. 0 equals 0 squared. So when u is equal to 0, t is equal to 0. On the inside, however, stuff changes just a little bit. Okay, u becomes t squared. So you have t squared now. But this t squared is a power of a power, right? So the square, the 2, is going to multiply with the x minus 1, and that gives you 2x minus 2. All right. And then this next term, not much is going to change, so except for the u becoming a t squared. And then we have our differential du, which becomes 2t dt. Okay, light work. This t and that, we can multiply those together, and the exponents add. So this is t to the first, so 1 plus this exponent right here becomes your new exponent. And I'm going to move the 2 to the outside. Should I do that? Yeah, let's just do that for now. Okay, 0 to 1. And this new exponent is t to the 2x minus 1. And that's that t and that 2 dealt with. And all that's left is this term to write down. And you can see why we made that substitution. Because everything suddenly looks like that again, right? Our bounds are the same. We kind of have this 2 coefficient on the outside. We can deal with that in a second. We have this part in the integrand. We just got to plug in z for y. And then we have this. We want to make that vanish. So how do we do this? Well, I'm going to copy this back up here again, and we can plug in some values for the beta function and see which ones make this identical to that. Okay, so I copied this back up there. I'm gonna slightly change this up too. Actually, no, let's just plug in some values. First of all, notice that this term just simply doesn't exist, right? So if we can make it equal to 1 by plugging in a certain value for x, that would be nice. If we zero out the exponent, right, anything to the 0th power is just equal to 1. So let's try to make the exponent 1. For 2x minus 1 to be equal to 0, x needs to be 1/2. So if we just plug in 1/2 for the beta function, for the x value of the beta function, that's that dealt with, because plugging 1/2 into there zeroes out this exponent, which makes this whole term 1, and that makes it disappear. And the second thing is, here instead of a y we have a z, so we're gonna just plug a z into the second input. So now this 2 on the outside is going to stay, but we have integral from 0 to 1. This first factor disappeared, and all we're left with is this second factor, z minus 1 dt. Okay. These integrals are now exactly the same. They're just named slightly differently, right? That one's named x, this one's named t. But they represent the same area, regardless of whether you call the axis the t-axis or the x-axis, the graph is the same. It represents the same area. So these integrals are now identical, except for this 2 right here. So what I'm going to do is I'm going to manipulate this one slightly. Let's pull out a 2, right? So if we have 2 times this integral, that would be nice. So we would reduce this power by 1 to be able to pull out a 2, right? So we pulled out a 2, and then now we have that integral. Okay, so this whole thing now is equal to beta of 1/2 comma z. So let's just go ahead and write that in there. Okay, but we want this in terms of the gamma function, right? Because notice that the Legendre duplication formula is all in terms of the gamma function. So we can use a property that we derived early, no, not derived, but I introduced earlier, and I might derive in a future video, of course. Beta of xy is equal to gamma of x, gamma of y, gamma of x plus y. So let's just replace this beta function and rewrite it in terms of gamma, right? So basically just replace all the x's here with the 1/2 and all the y's here with the z. And voila. Okay, so we found out that this guy is equal to that guy. Now, so I'm going to copy this all down again. Gamma squared of z over gamma of 2z is equal to 2 to the 1 minus 2z. So we already have this exponential here, times, now this guy, gamma of 1/2 is famously equal to square root of pi. And if you wanted to figure that out, what you would do is plug this 1/2 into the definition of the gamma function, the integral, right? And then solve that integral. You're going to need to make a substitution. You're going to need to do integration by parts. After that, use the Gaussian integral, right? The Gaussian integral is equal to square root of pi. You'll find that this is identical to the Gaussian integral. So long story short, I'm just going to put down square root of pi there. You have the gamma of z, and then you have the 1 over, you have this stuff, right? So you can see that we're basically done, because cancel this square with this whole gamma, dividing both sides by gamma, basically, and then multiplying this on both sides, and then multiplying this on both sides. So this thing's going to end up in the numerator here, and it's going to end up being the only thing in the numerator. And this thing is also going to end up in the numerator here. Okay, so there you go. That right there is the Legendre duplication formula, identical to what we have up here. Actually, no, we're missing a gamma of z up here. I only canceled the square. There's one more gamma remaining. So this is what we're looking for. So we're going to use that now, but how, right? To be able to leverage this. So we want to find something that's going to have this form on the left-hand side here pop up. Okay. So, how do we do that? Well, notice that we don't have any gammas that are multiplying right now, but we can make it multiply, right? Just multiply gamma on top and on the bottom, and we're set. But gamma of what? Well, currently our goal, notice that our final answer doesn't have a gamma in the denominator, so we want to get the gamma out of the denominator, right? So if this is our z, right, s over 2, then the thing that we want to multiply on is a gamma of 1/2 plus z, which is 1/2 plus s over 2, which is, so onto this thing, we're going to multiply a gamma of 1/2 plus s over 2. And that is what is going to let us take advantage of the Legendre duplication formula in the denominator. But we have to do it on top too, and there's a simpler way to write this, right? 1 plus s over all over 2, just because they have the same denominator, obviously. Okay, so the top we also multiply by 1 plus s over 2. Okay, so notice that there's conjugate pair for these gamma functions, which is pretty interesting. But for now, I just want to deal with the bottom. Okay, so the top's going to stay the same. I'm going to copy it down. I'm going to move these gammas out to the side, move this pi up to the front. Okay, and in the bottom, we have this exact form right here, gamma of z times gamma of 1/2 plus z. So let's just replace it with this, right? Except z is s over 2, but you get the point. Here we have 2 to the power of 1 minus 2z, but z is s over 2, so obviously these 2's cancel. You just get 2 to the 1 minus s. 1 minus s, right? Okay, square root of pi is just going to be there. And the gamma of 2z, z is once again s over 2. So 2 times s over 2 is just s. So we have our old friend gamma of s back. Alright, and that's it for the Legendre duplication formula. Now we have to use more formulas to be able to do the rest of our manipulations, right? First of all, though, we can move everything that we don't need to be down here up into the top, right? First of all, notice that square root of pi is just pi to the 1/2, right? So this, we have pi to the s minus 1/2 over pi to the 1/2. So because this is in the numerator and this is in the denominator, the exponent is going to subtract. So we have s minus 1/2 minus 1/2 again. So that's just going to give us pi to the s minus 1 instead. And then this too is going to, if we want to put it up in the numerator, the exponent is going to have to be negative. So that just reverses the order of subtraction. S minus 1 instead of 1 minus s. Next you have zeta of 1 minus s. And then you have these two gamma functions and then the third gamma function in the denominator. Okay, so I would argue that this looks slightly better now because the gamma function in the denominator is simpler, right? The argument is not s over 2, it is instead s. But we still have to get rid of it. But before we do that, notice that there is this cool conjugate pair right here, right? So maybe we can do something with that first, and maybe that'll help us get this shit out of the denominator. Okay, well, now, what is another identity that comes from two gamma functions multiplying together? Well, that is Euler's reflection formula, which I can prove, but I'm not going to right now because there's probably like loads of other shit on the internet proving Euler's reflection formula. But it goes like this: gamma of z times gamma of 1 minus z is equal to sine of, let me think, sine of pi, there's a sign in the denominator. It's pi over sine of pi z, like that. It looks kind of weird, but it's provable. How are we going to use it though? Well, notice that if we let z equal to 1 plus s over 2, right? 1 plus s over 2. Well, we just got to calculate 1 minus z, which is 1 minus 1 plus s over 2. 1 is just 2 over 2. And you can distribute this negative sign into both of these terms in the numerator. So you get negative 1 minus s. This 2 minus 1 gives you 1, right? And then you still have this negative s left, so you just have that. So, all in all, if z is 1 plus s over 2, like that, then 1 minus z is the conjugate, right? As we calculated. It is 1 minus s over 2. And that is still going to be equal to pi over sine of pi times your z, which is 1 plus s over 2. Which we'll find a way to deal with later. Okay, so this guy right here in the denominator, you can split it up and then take advantage of a property. But yeah, we now have this for a fact, right? So we now know how to replace this conjugate pair right here. We replace it with this pi and then this trig function. So that's where the sign comes from, kind of where the sign comes from, right? Because we still got to deal with some stuff before we fully get to that form. And that is splitting this guy up. Let's just deal with the denominator, right? Sine of pi times 1 plus s over 2. If you just if you split up the fraction, this becomes 1 half plus s over 2, right? Sorry, s over 2. And this pi multiplies both of them. So if you just multiply it in, you get sine of, this first term is going to become pi over 2, and then this last term is going to become pi s over 2. Sine of pi over 2 plus anything is just cosine. Okay, yeah. So this still gives you cosine of your other term. Because trig stuff, and you can expand this using the sine angle sum identity, and it'll give you cosine of pi s over 2. Okay? Yeah, okay. Now, we gotta plug it all in. So, before we do that though, this denominator we can just completely replace with cosine of pi s over 2. All agree? Okay, so this conjugate pair, we can now go ahead and replace it. I'm going to copy basically everything else down first. Notice that if we replace that guy with this guy right here, I'm going to box it because it's important, the pi ends up in the numerator. This pi ends up in the numerator. If we multiply that with this pi to the s minus 1, the negative 1 disappears. You just get pi to the s. Right? And you still have this 2 to the s minus 1 here. And then pi to the s. So You kind of have what's going on up there now, just the exponents are flipped, but that's going to come later, once again, later. And then I'm going to write down this zeta of 1 minus s. Okay, this right here, we already dealt with the pi, but now there's a cosine of that thing in the denominator, so might as well just write that in the denominator, right? In the numerator, there's not much left. So we just have gamma of s times cosine of pi s over 2. Okay, that's very nice. So there's a cosine in the denominator, kind of odd. But there's one more spot where you can use Euler's reflection formula. And if I'm gonna copy this stuff back up there, and then we'll move on in a second. Okay, so we've gotten to this stage. A lot of people stop around here somewhere, but you can keep going and get to this final form. How do we do that? Well, this gamma of s is in the denominator. And as I said earlier, we're going to be taking a look at the Euler's reflection formula again. This time we're going to apply it slightly differently, right? Because notice we have all of this junk. But if we wanted to go ahead and replace it, we just got to isolate 1 over gamma of s, because that's exactly what we have going on here, right? So to isolate that, we multiply this sign on both sides. So we still have this gamma of 1 minus z. Now we have a sign up here too. Not pi x, pi z. And we divide this pi on both sides. And then, in fact, I'm going to write this over pi as pi to the negative 1, because it'll help us with dealing with that. Honestly, I don't know. It doesn't make a big difference. Pi to the negative 1. All right, on this side, all we need to do is divide gamma of z. So we get 1 over gamma of z. All right. So basically just replace this with that, right? Now, basically almost everything is in the numerator, right? We don't need to worry about any of that anymore. We just have this cosine to deal with. Now, you may be thinking we can turn this cosine into secant, but let me give you a hint. This sign up in the numerator, we can do some trig identity work. So all in all, you now in the numerator, you now have all of this stuff, which I'll copy down. And before I do that, actually, this pi to the s, we now have a pi to the negative 1 being multiplied too. So the exponents are going to add. S plus negative 1 is just s minus 1. And then the zeta, and then the rest of this stuff. So we have gamma of 1 minus z sine of pi, not z, s, because like this is almost the same as that. It's just that here all of our arguments are s instead of z. Sine of pi s. And yeah, we just replaced that, right? So in the bottom, all we're left with is a cosine of pi s over 2. Now this is really simple, because what you can do is expand out that sine of pi s. If you recall the sine double angle formula, sine of 2 theta, this is just 2 sine cosine, right? How can we use that here though? We have a pi times s, not a 2 times s, theta, whatever. Go ahead and replace all the thetas in here with the theta over 2. Replacing this guy with the theta over 2, you get 2 times theta over 2. So the 2's cancel, you just get theta. So you now have another expression for sine. Here on the right hand side, it's a very basic replacement, right? All the thetas become theta over 2. But yes, you now have your identity. If you go ahead and replace all of these thetas with these pi s's, then we can expand out this guy. So I'm going to copy all this down again, but expand out this. All right, so sine of pi s, just plug up, it's just this exact form, right? The second row right here, except all the thetas we can go ahead and replace with the pi s. So sine of pi s is equal to 2 sine of pi s over 2 cosine of pi s over 2. And finally, we are able to get the last object out of the denominator, which is a cosine of pi s over 2. These guys cancel. So what are you left with? Well, first of all, you can simplify something. This 2 to the first times 2 to the s minus 1, the exponents add once again. S minus 1 plus 1 gives you just s. So all in all, I'm going to write this down all in one line. This zeta of s, I'm going to copy it down again. On the right-hand side, you have 2 to the s, right? Because this 2 kind of canceled with this -1. And then we have this pi to the s minus 1. We have, I'm going to put it down in the right order. I'm going to put the sign down first. Sine of pi s over 2. Then we have our gamma. And all that's left is to write down our other zeta. And there we go. We proved it. We used a lot of different identities and a lot of weird manipulations, uncalled manipulations. But at the end of the day, we got what we were setting out to look for. So that's pretty cool. Yeah, that's it. This right here is our identity proven. So I'm going to put a shaded box and I'm going to leave it up to you guys to look at and gawk at, because that is so unbelievably cool, right? Like, it's just so weird to think of where this pi to the s minus 1 could have come from. Like, zeta of s is just an infinite series, right, with weird exponents. Where did the sign come from? The exponential, the pi to the s minus 1, right? But yeah, that's it.